Hi guys, welcome again to my channel. My name is Malasa. Today I'm gonna be show you the detailed designing of the shear wall of this 20-story building using ETABS 2016 as per the Ethiopian and European building code of standard. As you remember, previously we have already shown you the detailed design parts of the beams of this 20-story building using ETABS 2016. So if you are a new comer for this channel, don't forget subscribe my channel so that you'll be getting more relevant tutorials which have been already prepared with reference to this story building. And also, if you are a member of my channel, don't forget providing me comments and questions regarding to the modeling and the designing of this 20-story building using ETABS 2016 as per the European and Ethiopian building code of standard. And if you want to get an immediate notification for the newly uploaded videos, you can press the bell icon. And don't forget also share my videos to your friends so that your friends will be getting more relevant tutorials regarding to the designing and the modeling of reinforced concrete structures and steel structures. So now let me proceed to the today's tutorials, which is tutorials part 20, which will be focusing on designing of shear walls. So before proceeding to the design part, now let me say something. What does shear wall mean, and what is its functions, and what is its orientation, and what is the behavior of shear walls in reinforced concrete structures. So now let me proceed to the PowerPoint. Okay, here, sorry. Okay, here now, as we know, shear walls are nothing but those are wall which is reinforced structure. So the main purpose of shear wall is just to resist shear, wind force, and the lateral force that causes the damage to building during the earthquake. Shear walls. Sorry. So here the main purpose of a shear wall is just to resist two forces. The first one is the lateral force, and the second one is the shear force. And which is this is the primary function of shear wall, and the secondary function of shear wall is just to resist also the gravity loads. That is gravity force. So, but all the primary function of shear wall is just to resist the lateral and the shear force. So the lateral force may be seismic, or it may be wind. So this is the primary function of shear wall. And when we come to the types of the shear walls, we'll have different types of shear wall. The first one is linear or rectangular shear. That means it is just like this. It is a plane or linear or rectangular shear. And the second one is flanger type shear. So we may have a flange at index of the rectangular shear, just like this. Here, this is a flange type shear. This is flanger type. It is flanger type, and this one is it is rectangular. It is rectangular. So the flange may be at one end, or it may be at two end, or it may be at three location. We may have a flange here. It depends on the magnitude of the stress. So the flanger shear is a combination of it is a combination of the C sharps, the I sharp, and the Z sharp, which is a combination of all those channel. What you call it? It is flanger type. And the third one is it is a core wall, which is basically used at the interior portion of the building, basically for the purpose of just the lifts. Now, here this is this can be located at the lift location. So this is a combination of also the channel like C, U, square, rectangles, or Z, just like this. We may have a core wall like this, and here this is the location of the lift, or it may be just it may be C type, just like this, or it may be square. This is rectangular, and it may be also square type, just like this, or it may be Z deformed. So the combination of channels will provide core wall. And the other is it is a coupling wall. So what does coupling wall mean? So coupling wall is nothing but just are two walls connected with a coupling beam, just like this. We may have one wall, suppose this is the elevation, and we may have another wall, just like this. This is wall 1 and this is wall 2. So we may connect them by beam at every floors. So this is what we call it is coupling beam. This coupling beam which connects to shear walls. And the other is rigid frame wall. That means the shear walls with column and beam at the interior portion, just like this. Here, this is suppose this is a shear wall, and here we may have a column here. So here we may have a beam, just like this. So here suppose this is a plan. So this wall, what you call it is a rigid framed wall, a combination of frames and walls. And the other is frame infill walls. That means this is also a combination of columns and beams with a wall. So just like this. We may have here suppose this is a plan of the building, and here we may have a frame just like this. Here this is a wall, and here we may have a column here, And here we may have a beam here. Just we may have a beam here. Here we may have a beam here. Just at every level of the story. And here we have a beam here, and here we have a beam here. Suppose here just we may have a column here. So the combination of frames and shear wall with the tie beam at the intermediate level of the story, which ties the shear walls at every floors, what you call it is framed infill wall, or its name is rigid. It is framed infill wall. So the inner the portion below the beam can be filled with concrete. And the other is barbell, or just it is with columns at index or at the intermediate depths. That means, suppose here we may have a rectangular wall just like this, and here just we may have a column here, that is C1, and we may have a column also here, that is C2, or we may have a column at the intermediate location, that is C3, and this one is shear wall, and this one is shear wall, and this one is column, and this one is column. So such type of wall, what you call it is barbell wall. That means shear wall combined with columns at its index or at its intermediate location. So this is the types of shear walls which can be used in high-rise buildings. So here we have now let me proceed to the structure form or the types of shear walls. We have already just discussed about the types of the shear walls. So the structural arrangement or the structural forms depends on the height to depth ratio. So the shear wall may be it may be short, or it may be squat, or it may be cantilever. So it depends on the height to depth ratio of the shear wall. If the height to depth ratio of the shear wall is less than 1, so the wall is called it is short wall. And if the ratio of the height to depth ratio is between 1 and 3, so the shear wall will be called squat wall. And if the ratio of the height of the wall to the depth of the wall is greater than 3, then the wall can be called a cantilever wall. So basically, it depends on the height of the structure. And generally, shear walls are either plain or flanged in section, while core walls consists of channels. We have already discussed about the plain wall, that means rectangular wall, and the flanged in section wall, that means having a flange at its ends, and also the core walls, which consists of a combination of channels. Here this is a plain wall, and this is flanged wall, and this is a channel wall, or what you call this core wall. This core wall. And now here we have the different systems of shear walls in reinforced concrete structure. So basically, we have 3 common lateral load resisting systems. So those are, the first one is the moment resisting frame, which is a combination of beams and columns without incorporating a shear wall. And here this one is the shear wall with at the right and at left sides, and also with a coupling beam which connects the shear wall at the intermediate locations or at each level of the story. And this one is beam. All those are beams which connects or which braces the shear walls. And this one is a braced frame system, which is a combination of shear wall, columns, and braces. Here we don't have any, and also we have beam here. So it is a combination of uh, beams, columns, and braces together with shear wall. Just this is the front view, and when we come to the plan view, just it looks like this one. This is basically it is the combination of column and beams, what we call this moment resisting frames. And when we come to here, it is a combination of shear wall, column, and beams. But the beams are provided at the interior portion of the building. Here we don't have any beam over the shear wall in this case. And when we come to here, just we have the collar, and here we have the shear wall, and here we have the slab. In both cases we have slab here. So here we don't have and also we have beam here. Just here we have the very beam which ties the of the very columns. And the other is now here shear walls are nothing but these are a vertical plate like RC walls. Generally starts at the foundation. Here it starts at the foundation and it ends at the roof level and goes through full building height. So we should not interrupt, or we should not uh, uh, interrupt the location of, or the height of, or just the continuity of the shear walls. So the shear walls has to be continuous, starting from the base of the building up to the roof, just like this. Here the shear wall starts at the base of the foundation and it ends to the roof level. So we should not disconnect, or we should not just stop the continuity of the shear walls through the height of the building. For example, if we extend these shear walls up to this point, and if we omit extending the shear walls up to the roof level, so it is not recommended to use such kind of arrangements. And now the main purpose and the main and the basic function of shear wall is the first one is for strength. That means it is for strength, and the second one is for stiffness. This stiffness, maybe it is the lateral stiffness. It provide lateral stiffness, or for torsional stiffness to increase the torsional behavior of the structure. And here we have also it increases the ductility of the structure. So those are the basic three functions of shear walls. Here now This is the graph which shows the deformability versus the strength of the shear wall. Here the yellow color is it is RC frame building, and here the other boundary, this one is for strength and this one is for stiffness. So the role of the shear walls: the smooth transfer of seismic forces and vertically oriented wide beam. That means it is used to transfer the seismic force from the floor slab to the shear wall, and also the shear wall will transfer the lateral or the seismic or the wind force to the foundation. So the main purpose is for the transferring of, for smooth transferring of seismic force or horizontal force to the foundation. So the orientation is vertical. And the advantage of shear wall in RC building, it is very good RCQ performance. So whenever there is a seismic or whenever there is a horizontal force or whenever there is a possibility of just increasing the total height of the structure, so we need to use shear walls. That is, in past RCQs, large number of RC framed buildings are damaged or collapsed because of the absence of shear walls. Shear wall buildings performed very well. So basically, whenever there is a large number of stories in a reinforced concrete structure, it is preferable to use the shear walls. And the advantage of shear walls in RC building, that means easy to construct, it is easy to construct, easily implemented at site, effective in reducing construction costs. So minimizing earthquakes damage to structural elements. Non-structural elements, example glass, windows, building, and contents. So this is the advantage of shear walls. And lesser lateral displacement than frames. So if we see, this is a moment resisting frame and this one is, it is a structure composed of shear wall. So just if we compare the lateral displacements of those two structures, the structure which is composed of the shear walls will have a small lateral displacement, but a structure which is composed of the moment resisting frame will have large lateral displacement. So the main purpose of the shear wall is to reduce the lateral displacements. And according to the architectural aspect, so when we see the location of the shear wall, it is preferable to locate the shear walls at the exterior boundary of the structure instead of just located at the interior portion of the structure. So this is just to increase the lateral stiffness and the torsional resistance of the structures. So here wall must be preferably the wall may be arranged in one direction or it may be arranged it may be provided in both directions. If the walls are provided in one direction, so it is advisable to use the moment resisting frame on another direction just to increase the lateral and the torsional stiffness behavior of the structures. If provided only in one direction, a proper moment resisting frame must be provided in the other direction. For example, we are providing this shear wall in X direction. So we are not providing shear wall in Y direction. So here we need to provide moment resisting frame along Y direction. Here this is the structure which is composed of shear walls and frames. And here the shear wall can extend over the full width of the buildings or even over partial width. That means here this is the width of the building. So RC wall of full width. So that is preferable to provide a shear wall for the full width of the structure. I mean the building, and extends the shear wall up to the top of the building. In this case, the shear wall is not provided for the full width of the building. Here, it is provided for half width of the building. So it is not advisable to provide. It may be for it may be provided for the full width, or it may be provided for the partial width. Walls should be throughout the height. That means here the wall which starts at the base of the foundation ends at the roof level. So we should not interrupt the continuity of the shear wall. So for example, if we see this one, there is a discontinuity of wall which is not advisable to provide such kind of arrangement. Here there is a discontinuity of this shear wall. So the shear wall starts at this level and ends at this level. It is not advisable to use such kind of provision. So this shear wall must be extended up to the base of the foundation. Walls should be throughout the height, cannot be interrupted in upper portion. That means here the reverse of the previous figure. That means here it starts at the base of the foundation and it must be finished at the top level. It should not be interrupted at this point. So this is the discontinuity of what not desirable. And here this is the best option, which starts at the base of the foundation and ends at the top of the building. And walls should be along the perimeter of the building. That means here we need to provide the walls along the periphery of the building. It is not advisable to provide shear walls as the interior portions, except whenever there is a mandatory provision of the core walls. Here, shear walls close to the center of the building are less efficient. That means the lateral and the torsional stiffness of this structure is higher than this structure. So this kind of structure will be translated laterally, or it will be subjected to the rotation. So in order to increase the torsional and the lateral stiffness of the structure, we need to provide the shear walls at the periphery of the building. And opening in walls must be as few as possible. So we should avoid using much number of openings in walls. As small as possible. That means the size must be also small. We should not use wider size of opening on walls, because those walls or those openings will reduce the effective cross-sectional area of the wall. And also as symmetry as possible, and we need to arrange the shear walls in symmetric manner as much as possible. So for example, if we see this building, large and randomly placed opening are provided on the faces of the wall. So we need to avoid using such kind of arrangement as much as possible. One, we need to reduce the size, and the second one is we need to use a small number of openings. And here, if we see this one, the arrangements are symmetry, the sizes are small. So this is the preferable arrangements of openings. And the placement of shear walls. Here, this is a good placement of shear wall, because we are providing at the periphery of the building, and here it is the fair placement of shear walls. That means it is located at the interior portion of the majority parts of the shear wall is located at the interior portion of the building. So this is not preferable just to arrange with such arrangement. And when we come to here, here we have the shear wall at the periphery of the building, and here we have a shear wall at the periphery of the building, but this one is uh, which is at the interior portion, so we need to reverse this orientation just like this. This is a poor arrangement, but this one is a proper arrangement. However, this one is a proper arrangement, and this arrangement will reduce the lateral and the torsional stiffness of the structure. So we need to reverse or rotate this 90 degree, and we need to arrange just like this. And when we come to this, here we are providing the shear at the internal portion of the building. So we need to avoid placing the shear at the interior portion. So we need to move this shear into this and this shear into this in order to provide a good arrangement and in order to increase the lateral and the torsional stiffness behavior of the structures. And when we come to here also, here just this shear wall is it is located in this direction, and this one is located in this direction. So that is preferable to rotate this shear wall into this direction. Sorry. So this one is this is a symmetric arrangement, and this one is a symmetric arrangement, and this one is not. It is unsymmetric arrangement, and this one is unsymmetric arrangement. So walls must be symmetric as much as possible. If we place these shear walls just like this, so it will be symmetric in one direction. And if we just provide also the shear walls just like this, and just like this, and just like this, which is drawn here, it will be symmetry in both directions. So the placement of the shear walls located symmetrically to reduce ill effect of twist. That means if the location of the shear walls is symmetric, then it reduces the twist or rotation. So symmetry can be along one direction or both direction. It may be along x direction, or it may be along y direction, or it may be on both direction. Can be located at the exterior or interior. That means shear walls, as much as possible, it is advisable to use at the exterior portion, but there may be a mandatory just to provide shear walls at the interior portion, especially the core walls. More effective where located along the exterior perimeter of the building. So here, this is the mode of failure. Here there is the horizontal force which is acting at the top of the structure. So this shear walls, this shear wall shows an overturning failure here. That means when we apply force at the top, the base of the shear wall raises up. This is what you call this overturning failure due to the vertical uplifting effect of the shear wall. And when we come to here, suppose here we are applying a lateral force at the top of the structure, and these parts of the wall translates or just moves toward the right side. So this kind of failure is called the horizontal sliding failure. And when we come to the third option, is suppose we are applying the lateral force at the top of the building, and this portion of here there is the crack at this portion. So this kind of crack will result in a shear failure. So here this portion is in tension, and this portion is in compression. So the tensile stress will exceed the tensile resistance of the section. In that case, the shear failure will happen. And now there is also undesirable mode of failure here. Suppose here we are applying here we are applying a lateral force at the top of the structure. So here these parts of suppose here this is the location of the neutral axis. This is the location of the neutral axis. So this portion is in tension, and this portion is in compression. So here there is the crushing failure and the flexure compression failure at this side. This is what you call this compression failure. So the section fails in compression. And here, if we draw the suppose here this is the stress strain diagram, and this one is the neutral axis, and here this portion is the compressive stress, and this one is the tensile stress. So this portion is subjected to the tensile stress, and this side of the shear wall is subjected to the compressive stress. So if the compressive stress exceeds 0.15, then it is advisable to provide a boundary element. That means, suppose we need to provide a boundary element here. This is L critical, and this one is L critical. So this is what you call this a boundary element. So we need to provide much number of reinforcement at the boundary element in order to increase the tensile and the compressive resistance of the section, so that the failure in compression failure will be avoided. So this is what about the just the failure in compression. Now here there is, the shear demand is higher at the base of the building or at the base of the structure, and it is small at the top of the structure, because the horizontal, the cumulative summation of the horizontal forces at every floors will provide the base shear. So shear demand is more in lower. Here there is the generated horizontal force at each floor level here. So every generated horizontal force will be transferred to what? To the shear walls, and the shear walls to the foundation. This is the smooth transferring mechanism of the horizontal force from the slab to the shear walls, from the shear walls to the foundation. So finally there will be higher base shear at the base of the foundation. So the foundation has to be, or the shear wall has to be designed for base shear. As we said previously, the shear wall has to resist the lateral force plus the shear force. And here region of the ductile detailing. Here, as we have already seen previously, there is yielding of vertical reinforcement here. So as the vertical reinforcement yields at this location, there will be a tensile failure. So how can we avoid this tensile failure? So we need to revise our design, or we need to increase the number of reinforcements per meter width, or the spacing of the reinforcement, or we need to increase the diameter of the reinforcement in order to increase the tensile strength of this section. And when we come to the right side, which is subjected to the compressive stress, just here there is no failure on the compressive, so the only failure happen at the tensile zone of the section. So we need to provide either the boundary element here, or we need to revise the spacing of the reinforcement. Here, when we come to here, also the ductile response region, which is this is so this is the critical height where we need to provide closely spaced loops or shear reinforcement at this location, because the base shear is high at the base of the structure, which leads to the failure in yielding of the silver. So this is also the geometry of the shear walls. Some of the shapes of the shear walls. Here, this is, as we have already seen, it is a plane, or it is rectangular form. And this one is, it is flanged form, that is L shape. And this one is, it is a C shaped, which is what we call also, it is flanged section. And this one is linear, and this one is corbel, basically used for lifters. And here the primary reinforcement in shear wall looks like this one. Here this one is for a shear wall without a boundary element. That means a wall which is subjected to insignificant stresses or tensile stresses and compressive stresses. So this is a uniform reinforcement arrangement. And this is a wall having a boundary element at ends. So here, as you see, the boundary element, the stresses are higher at the extreme or at the ends of the shear wall. So in order to accommodate the effect of the stresses at ends of the shear wall, we need to provide the boundary element. So the arrangements of the reinforcements at the boundary element, it's completely different from the middle region. So the middle region needs minimum reinforcement, while the two ends of the shear wall takes 100% of the required reinforcement. That is, half of the required reinforcement can be located here, and half of the required reinforcement has to be provided at this region. And also the confined corpus must be also provided with the proper spacing. So we can just design the boundary element like a column, just like a column. So here, closely spaced confining reinforcement in the boundary element, that is the stirrups. So the maximum and the minimum spacing of the hooks are provided in the body. Here, this is the confining steel in boundary element, and this one is for thin section. If the thickness of the wall is it is very thin, so we can provide the vertical reinforcement in one layer. If the thickness of in a thin shear wall, we may provide a boundary element here. This is what we call, it is a boundary element. So when we provide a boundary element where the stress limit, the stress exceeds the stress limit, that means 0.1. If the stress in the boundary in a shear wall exceeds the limiting stress, which is 0.15, then we need to provide shear walls. We need to provide the boundary element at the location where the stress exceeds the stress limit. If the tensile, the compressive stress doesn't exceed the compressive stress limit, so no need of providing the boundary element. So this is for thin shear wall having a single layer. And when we come to the thick wall, so in thick wall we need to provide two layer of vertical reinforcement. That means at both we need to provide vertical reinforcement at both faces. So this is for the condition where there is no need of the boundary element. And in this case, we need to provide the boundary element here. Here, the boundary we need to provide the boundary element in order to accommodate an excessive stresses. So this the length of the boundary element. This length provided in the code, and we will see later during the design of the shower. And also here this size, this width is the minimum width is specified in the code, and we will see it also later. So here we'll have also the ties. We need to provide ties at the intermediate portion of or at the wave of the wall in order to accommodate the excessive shear in a shear wall. So here we are using open leg ties, and here we are using a closed loop ties here. So the provision of ties must follow the provision of collar, because shear wall can be designed as a collar, as we have already said. So the spacing between this and this should not exceed 200 millimeter for medium ductility class. Just we can consider, we can follow the design principles of collar. And here, when we see the detail of this open leg ties, just it looks like this. And when we see the detail of these closed loop ties, it looks like this. So we need to use the ties whenever the main vertical reinforcements exceeds the minimum amount of vertical reinforcement which is provided in the code. So in that case, we need to use the ties, extra ties. This is all about the today's tutorial, which we're focusing on the definition and the description, as well as the behavior and the locations of the shear wall in high-rise building. So if you are a new member for my channel, don't forget subscribe my channel so that you'll be getting more relevant tutorials which have been already prepared with reference to the modeling and designing of this Tuoni story building. So if you are also the member of my channel, don't forget providing me comments in my commenting boxes so that I will be acting as much as possible within a short period of time. And also, if you want to need an immediate notification for the newly uploaded videos, you can press the bell icon. And also don't forget share all my videos to your friends so that your friends will be getting more relevant tutorials which have been already prepared with reference to this Tuoni story building. This is all about the today tutorials. We'll meet on tutorial part 21, which will be focusing on the detailed designing parts of the shear wall with reference to this Tioni story building. See you next time. Bye bye.